So have you ever spent hours, and I mean hours, carefully calculating your subnets on paper, feeling like an absolute math genius, only to type those IP addresses into your router and get immediately hit with a glaring error message? Yeah, we've all been there. It's basically a rite of passage for almost every networking student, and honestly, the culprit is usually Variable Length Subnet Masking, or VLSM for short. Today, we're going to demystify this critical networking concept in this explainer. We'll show you the exact trap that catches almost everyone and give you the fail-safe methods the pros use to design networks that actually work in the real world, not just on a whiteboard.
Okay, let's dive into this. Here is our agenda for today. 1. The power of VLSM. 2. Classless routing protocols. 3. A common subnetting mistake. 4. Finding VLSM overlaps. And 5. Adding subnets without overlap.
Section 1. The power of VLSM.
To really grasp the power of VLSM, we first need a rock-solid definition. Variable length subnet masking simply means using more than one subnet mask for different subnets, but, and this is absolutely key here, within a single classful network. That means inside one class A, B, or C address block, like a 10.0.0.0 network, you aren't forced to just use one uniform mask size for the whole shebang. You can essentially slice that pie into totally different sized pieces based exactly on what each specific location needs.
Now, you might be wondering, why go through the mathematical hassle of doing this? Well, because the benefits are massive. First off, it allows for incredibly efficient use of your assigned IP address space. Think about it. If you have a point-to-point serial link that only needs 2 hosts, you do not want to waste an entire subnet of 254 addresses on it. That's just throwing IPs away. VLSM prevents that waste entirely. Plus, it allows for powerful route aggregation. This means a router can summarize a bunch of smaller subnets into one single advertisement, which keeps the routing tables at the backbone level super clean and blazing fast. And keep in mind, these principles apply beautifully to both IPv4 and IPv6 network environments.
Section 2. Classless routing protocols. And this brilliantly illustrates the reality of the server room. You can have racks upon racks of the most expensive routing hardware in the world, perfectly wired up, but without the right software protocol talking across those wires, VLSM literally will not function.
So let's look at exactly why that is. Take the legacy protocol RIP version 1. It is a classful routing protocol. It does not send the subnet mask in its routing updates. So if a router receives an update about a network without a mask, it has absolutely no idea if it's looking at a /24, a /30, or something else. It's totally blind to your custom sizes. But modern, classless routing protocols, things like RIFP2, EIGRP, and OSPF, they do send the mask with every single update. That right there is the foundational requirement for VLSM to operate.
Section 3. A common subnetting mistake. Imagine this scenario for a second. You're given a network prompt. You need a network for 2 hosts, another for 8 hosts, one for 30, and maybe one for 100. So you start calculating. You map everything out perfectly on paper. Then you go to configure your router's gigabit interfaces, you type in the IP and mask for your second subnet, and bam! The router immediately throws an overlapping network error. Why in the world did this happen when your math was flawless?
So the crucial point is how binary math interacts with block sizes. The classic candidate trap here is starting with the smallest networks first. Say you assign those little /30 point-to-point links right out of the gate, and then you try to build up to that big network that needs 100 hosts. Well, because of the way binary boundaries work, if you don't align large blocks to their specific binary multiples, you end up creating mathematical remainders. The router calculates the required network ID for that bigger block, forces it backwards to align with a zero boundary, and suddenly, it's trying to overwrite the small subnets you just created. The pro method to fix this is incredibly simple. Whatever list of requirements you are giving, always, and I mean always, choose the largest block of host first and work your way down. No remainders, no router rejection.
Section 4. Finding VLSM overlaps.
Now, what's really interesting about this is how we can visualize the reality of IP allocation. I like to think of a classful network as a giant block of wood. If you carve out a large piece for a /22 subnet, you cannot mathematically use any of the smaller /23 or /24 blocks that fall inside that physical space. It's gone. Choosing one subnet instantly disables and blocks out overlapping ranges in different columns of your subnetting plan.
And the stakes are seriously high here. If you accidentally implement overlapping subnets, it's not just a cute little warning light on a dashboard.
It means routing tables have overlapping entries, which causes routers to try and assign identical IP addresses to entirely different geographical locations. When that happens, packets get lost, hosts can't communicate, and the network just essentially breaks down. To prevent this absolute disaster, we rely on a highly structured, fail-safe procedural method. Cisco recommends a strict three-step process for spotting these overlaps before they break your network. Step 1. Take your list of IPs and calculate the exact subnet ID and the broadcast address for every single one of them. This gives you the full real estate of those addresses. Step 2. Reorganize that list so the subnet IDs are in strict numerical order, from lowest to highest. And Step 3. Simply scan down the list, comparing one range to the one directly below it.
When you do this, the math reveals the truth perfectly. Let's look closely. The first network goes from .0 to .3. Clear enough. The next network, a /27, starts at .32 and goes all the way up to .63. But actually, look closely at that third entry. It's a /30 that also starts at .32 and goes to .35. Because we laid out the full range from subnet ID to broadcast address, it is glaringly obvious that the third subnet is completely swallowed up by the second one. That right there is a massive overlap.
Section 5. Adding subnets without overlap. So how do we build onto an existing network without breaking it? To do this flawlessly, we use a master 5-step process. First, determine the mask length you need based on your host requirements. Second, calculate all the possible subnets for that mask within your classful network, just acting as if the network is totally empty. Third, make a list of all your currently existing subnets. Fourth, compare your list of possibilities to your list of existing networks and ruthlessly cross out any candidates that overlap. And finally, step 5, you just choose one of the remaining safe subnets.
Let's move to a real-world scenario and see how this builds out. Let's say we need a new /23 subnet. We generated our candidate list here, .0, .2, .4, .6. Then we cross-referenced it with our active network. As we can easily see, .2 is out. It overlaps the router 1 LAN. .4 is out. It clashes with router 2. .6 is dead in the water. It hits router 3. By crossing out those unavailable blocks, the safe answer just isolates itself.
And there it is, 172.16.0.0. By using a strict, structured methodology, we found the numerically lowest, perfectly valid subnet ID that we can configure with absolute confidence. No guessing, no crossing your fingers and hoping for the best, just solid, undeniable networking logic. So we've broken down why VLSM is necessary, exposed the huge trap of starting with small block sizes, and learned the step-by-step methods to hunt down overlaps and safely expand our designs. The concepts are totally sound, and the math works perfectly. The only question left is this. The next time you face a VLSM challenge, are you going to rely on guesswork, or are you ready to use this structured methodology and prove your design right on the router interface? Thanks for joining me to demystify VLSM. Keep calculating, keep verifying, and I'll see you in the next explainer.